Let's use a water bottle like this one to explain how water isotopes might change in the environment. So here's a bottle. Let's say it's half full of water. Top half of the bottle contains air, bottom half has the water, and the water will have a whole bunch of different water molecules. It'll have the lighter molecules, which will have oxygen 16 and hydrogen 1. It'll have some molecules which are a bit heavier, so it'll have either an oxygen 18 or 2 hydrogen. And there'll be some molecules that will have both. That'll be very rare. There'll be some that have both 2 hydrogens and 18 oxygens. It turns out that the lighter isotopes are more likely to take place in chemical and environmental reactions, and the water in the bottom half of this bottle, well, some of it will turn to vapor, and it will go and vaporize and go into the upper half of the bottle in gas phase. And it's the lighter isotopes that are going to go into the upper half, into the gas phase, because they're lighter. So in the water vapor, in the top half of your bottle, you'll see more of the 16 oxygen, and in the water and the bottom half, you'll see more of the 18 oxygen. And in the upper half, you'll see more of the 1 hydrogen, and in the bottom half, you'll see more of the water molecules with the 2 hydrogen. And because the top is open in this bottle, the vapor that's formed in this upper part here can escape, and it can leave the bottle and go out into the wider atmosphere, which means that this fractionation process can keep on going. There'll be more water that comes from liquid phase into the gas phase, and as it goes into the vapor, it's more likely that this is going to be the lighter isotope again. So over time, the water molecules that are left down here in the bottom half in the water phase, these are going to get isotopically heavier and heavier and heavier, or more positive. You get more of the heavier isotope. And the water molecules that are going to go in the vapor phase are going to get more negative. There's more of the lighter isotope that's been vaporized. And what we can do now is put the lid on. We can remove the lid from here, put it onto the top, and then we stop the reaction, and the vapor can't escape anymore into the wider atmosphere. And then the bottle will reach an equilibrium. There will still be more of the lighter isotope in the gas phase in the top half, and there'll still be more of the heavier isotopes in the liquid phase in the bottom half, but the reaction can't go any further because you can't lose any of the isotopes out of the bottle. The drinking water bottle with the lid on is like the whole Earth. The water's trapped within the Earth system, it's not going anywhere. So that could explain how the Earth is working at a global scale. And the bottle with the lid off is more like a local process. Maybe it's a lake or a water body or a river where the water can vaporize into the atmosphere and it can go off into the wider atmosphere, and the process can keep going. So now we can look at how water moves from the ocean into the atmosphere from evaporation, forms clouds, and then comes back to land as rain, and we can put some isotope values to those processes. So initially in the ocean, on the left-hand corner, the isotope composition of the water is the same as the standard, because the standard is the ocean water and the values are 0. As we get evaporation of that water, same as in the drinking water bottle example, we'll have more of the lighter isotopes in the water vapor. So we will see here that the vapor in the atmosphere has a negative value, meaning there's more of the oxygen 16 compared to oxygen 18 and more hydrogen 1 compared to hydrogen 2 than you would have in the ocean water and the standard. If that vapor forms clouds and rain falls from the clouds, then it's going to be the heavier masses that are more likely to fall as rain. And so the composition of the rain is less negative than the vapor. And as the rain and clouds evolve and go further and further from the original source, you'll find that the vapor starts to get more and more negative because it's losing the heavy isotopes as rain. And as the rain goes further and further inland, the rain isotopic composition gets more and more negative because the more positive isotopes have already fallen on the land surface back over here. And this keeps going until there's no more water vapor left in the atmosphere. So now we can use isotopes to make maps. And this is a map of the isotopic composition of leaves. Scientists have gone around the world and collected leaf samples and extracted the oxygen from the water in the leaves and that tells us something about the water that the trees were using when they were growing. And the reasons why they do this is that then we can go back and look at leaf samples from the geological past and then see how the climate might have changed in the past compared to today. So this is the modern day, and you can see that we have some very red values, which are the more positive isotopes. So there's more of the oxygen 18 in these leaves, and these are mostly situated in dry, arid regions. So I would expect there's more evaporation in these regions. We've got the desert interior of Australia, for example, and the Sahara. In these regions, the water that the trees were accessing has evaporated already. It's lost the lighter isotopes into the atmosphere, and it's the heavier isotopes that are remaining, which the trees can access. In other parts of the world, the isotopic composition is very negative, and this is mostly towards the poles. So here are the high latitudes, the blue values, and also some here towards the tip of South America. So in these regions, the water vapor has been transported for the longest distance from its source. It starts in the oceans, it's rained a lot, and by the time the weather systems get as far as the North and South Pole, the only water that's left there is going to be the isotopically lightest material with the predominance of oxygen 16, and it's that water that the trees are going to take and use in their leaves. And here's another map showing hydrogen and oxygen isotopes in the USA, but I haven't told you what it's a map of. So what do you think the oxygen and hydrogen isotopes have been extracted from, and why is it interesting?